Hi everyone. In the last section we looked at one model of an observation that shows the particle nature of light. In this section, 9.2, Compton scatter, we'll look at another interaction which is described by the particle model. So in Compton scatter, what happens is that a photon scatters off an electron, and the scattered photon has a longer wavelength than the incident photon. Scatter itself can happen for waves, but this change in wavelength can only be described by a particle interaction. So let's look at what happens. We have an initial photon, which is incident on an electron. The electron then recoils, and it leaves with some of the initial energy and momentum of the photon so that it has a velocity. The scattered photon then has lost energy, so now it has a lower energy and a longer wavelength. And we can see that the energy is inversely proportional to wavelength through E equals hc over lambda. So in general, the formula for the difference between the wavelengths from the incident photon to the scattered photon is called the Compton shift, and it looks like this. Lambda prime, the scattered photon wavelength, minus lambda, the incident photon wavelength, equals h, Planck's constant, over m, the mass of the electron, c, the speed of light, times 1 minus cos phi. Notice here that phi is the scattered angle. Don't confuse that with the work function that we used in the previous section. So just another note about this is that these speeds can be relativistic. The electron can scatter at a relativistic speed after the collision. And this formula here is derived from assuming that momentum and energy are both conserved during the collision. Okay, let's try the first example. X-rays with an energy of 300 keV undergo Compton scattering at a target. The scattered X-rays were detected at 37 degrees relative to the incident rays. Find A, the Compton shift at this angle, B, the energy of the scattered X-ray, C, the energy of the recoiling electron. Okay, so let's have a look at part A. We want to be able to find the Compton shift. So in order to do that, we are going to eventually need the wavelength of the incident photon. So let's find that now. So using E equals hc over lambda, we have lambda is hc over E. And plugging in Planck's constant times the speed of light, 3 times 10 to the 8, over 300,000 electron volts, and then we do need to convert that to joules just to match the units of Planck's constant. So times 1.602 times 10 to the negative 19 joules per eV equals 4.14 times 10 to the negative 12 meters. We'll actually use that in part B, but let's go ahead and calculate the Compton shift. So lambda prime minus lambda, scattered wavelength minus initial wavelength, equals h over mc times 1 minus cos phi. And then again, plugging in the constants here, we have Planck's constant over the mass of the electron, and then c, the speed of light, all in SI units here. 1 minus cos 37 degrees gives me 4.88 times 10 to the negative 13 meters. Okay, I'll just pause and erase so that we can do part B. Okay, so in this part, we were asked to find the energy of the scattered photon. So using the initial wavelength that we found already and then the Compton shift from part A, we can just add those to find the final wavelength of that scattered photon. So we have lambda prime equals lambda plus delta lambda, and adding those two numbers gives 4.62 times 10 to the negative 12 meters. Then we can plug it into the formula for the energy of the photon, which is E equals hc over lambda. Planck's constant times c over that wavelength we just found gives 4.3 times 10 to the negative 14 joules, which we can convert to electron volts using the conversion I did in part A, again, to give 269 keV. Okay, now in part C, what we're looking for is the energy of that recoiling electron. And since energy is conserved, what happens is that photon comes in with an incident energy, and then part of its energy goes to the recoiling electron, and part of it goes to the scattered photon. So we can subtract. The kinetic energy of the electron will be the incident energy of the photon minus the scattered photon energy. So 300 keV minus 269 keV, which gives 31 keV. There is another process that can occur when radiation is incident on a metal target. If that incident photon has sufficient energy, what can happen is that it approaches the metal and it essentially disappears and produces an electron and a positron in its place. So the positron is a form of antimatter. It's the antiparticle to the electron. It is identical except for its charge. It has a positive charge. So the reaction looks like this. Generally a gamma ray, which would be the highest energy form of electromagnetic radiation, or an X-ray, will then convert into a positron and an electron. So you may not have heard of a positron before because they generally don't exist very long in matter. What will happen is that the positrons will then recombine with other electrons in the material through positron annihilation. In positron annihilation, the positron will combine with another electron and then produce either 2 or 3 photons in its place. So it would look something like this. The electron and the positron combine and then produce photons, so essentially the reverse of pair production, though it can be 2 or 3 photons. And this is what's used in PET scans. So in PET scans, a radiopharmaceutical that emits positrons would be ingested, releasing positrons in the body that then combine and produce these 2 photons, generally gamma rays. So the time of flight for those photons to reach a detector is recorded and gives information about the processes and structures within the body. All right, let's do 2 examples now. Okay, what is the minimum energy of a photon required to produce an electron-positron pair? And what is the wavelength of such a photon? So I'd suggest you pause and then try that example. All right, let's look at the board. So in order to just produce a positron and an electron, the energy of the incident photon has to supply at least the rest energy of each particle. So that incident photon energy must be equal to the electron mass times c squared plus the positron mass times c squared. Since these particles are identical except for charge, they do have the same mass. So we have 2 times 9.11, the mass of the electron, times 10 to the negative 31 kilograms, and then times c squared, which gives 1.64 times 10 to the negative 13 joules. The next part we're asked for the wavelength that would correspond to this photon. So we have E equals hc over lambda, and we can rearrange to find the photon wavelength. Lambda is hc over E. So Planck's constant times the speed of light over that energy we just found gives 1.21 times 10 to the negative 12, and that is meters. And if you were to look this up on the electromagnetic spectrum, you would see that this is a gamma ray. Okay, one more example for this section. An electron and a positron accelerate towards one another so that they are moving at point 6 c when they collide. Find the energy and the frequency of the 2 photons produced. Okay, so this example looks something like this. We have both particles, the positron and the electron, moving towards each other with equal speeds but in opposite directions, colliding and then producing 2 annihilation photons. Because the initial velocities of the electrons are equal and opposite of the electron and the positron, and they have identical mass, we know the total initial momentum is 0. Momentum is conserved, so that means that the final momentum of the system must also be 0. So these 2 photons must have equal momentum after the collision, and then their energy would be pc, momentum times the speed of light, so their energy must be equal as well. So this is telling us basically that the energy of one incident particle, either the positron or the electron, since they would be identical, equals the energy of one photon after the collision. So we can calculate the final photon energy by using the energy of the electron, gamma, mass of the electron, c squared. So me c squared times gamma, we have the mass of the electron, 3 times 10 to the 8 meters per second squared, over 1 minus 0.6 squared, since the speed was 0.6 c. Okay, and that gives us an energy of one photon as 1.02 times 10 to the negative 13 joules. Then we can find the wavelength using the relationship, or find the frequency, sorry, using the relationship E over H. We could find the wavelength as well if needed, which is that energy we just found over Planck's constant to leave us with 1.54 times 10 to the 20 hertz.